Introduction to constraints in mechanics. A constraint is a restriction on the motion of a system. These can arise due to geometry, contact with surfaces, or imposed external conditions. Constraints are broadly classified into holonomic constraints, non-holonomic constraints. Let us now talk about holonomic constraints. A holonomic constraint is a constraint that can be expressed as an equation involving only the coordinates and, possibly, time. Here, q1, q2, qn are the generalized coordinates of the system. The key characteristics are 1. Integrable. Can be reduced to a constraint on coordinates. 2. Reduces degrees of freedom. 3. Leads to configuration space restrictions. Let us now talk about non-holonomic constraints. A non-holonomic constraint is a constraint that cannot be expressed solely in terms of coordinates and time. It often involves velocities and is non-integrable. Mathematically, the key characteristics are 1. Velocity dependent. 2. Not reducible to coordinate-only constraints. 3. Typically appear in rolling, sliding, or robotic motion. This table presents a comparative overview of holonomic and non-holonomic systems in classical mechanics. Holonomic systems are characterized by constraints that depend solely on the system's coordinates and time, making them integrable and capable of reducing the system's degrees of freedom. Typical examples include a pendulum or a bead sliding on a wire, and their constraints are expressed as equations of the form of q2, qn, time, equals 0. In contrast, non-holonomic systems involve constraints that depend on both coordinates and velocities, rendering them non-integrable and generally incapable of reducing degrees of freedom. Examples include rolling wheels, skates, and car motion, with constraint equations typically written as a function of q dot and time equals 0. This distinction is fundamental in understanding the behavior and control of mechanical systems. Why do constraints matter in mechanics? Holonomic constraints allow us to reduce the problem to fewer coordinates, simplifying analysis. Non-holonomic constraints require special methods. For example, Lagrange multipliers for non-holonomic systems. Essential in robotics, vehicle dynamics, control theory, and analytical mechanics. An example of a holonomic constraint. The diagram illustrates a simple pendulum system, consisting of a weight suspended from a fixed pivot point labeled O, by an inextensible string of length. The pendulum swings in a vertical plane, forming an angle theta with the vertical axis. The position of the weight is defined by coordinates x and y, which vary as the pendulum oscillates. This setup exemplifies a holonomic system, where the constraint, namely, the fixed length of the string, can be expressed as an equation involving only the system's coordinates and time. Such constraints simplify the analysis by reducing the degrees of freedom, making the system amenable to classical methods in analytical mechanics. An example of a non-holonomic constraint, a multi-body wheeled system. The image depicts a planar linkage mechanism composed of 3 interconnected rods colored yellow, red, and blue, each of length divided by 2. Joined by rotational joints. The configuration is defined by angular parameters alpha 1, alpha 2, and theta, which govern the orientation of each segment relative to a reference axis. Velocity components such as sine theta plus alpha 1, and cos theta plus alpha 1, and similar expressions for the other rods highlight the system's kinematic relationships. These trigonometric terms suggest that the motion of each rod is influenced by both its angular displacement and the overall rotation of the system. Such a setup is typical in robotic arms or mechanical linkages, where precise control of velocity and position is essential for coordinated movement. The variational principle in classical mechanics offers a remarkably elegant framework for understanding the motion of physical systems. Unlike Newtonian mechanics, which emphasizes forces and accelerations, The variational approach asserts that a system evolves between 2 points in time by minimizing or rendering stationary a specific quantity known as action. This action is defined as the time integral of the Lagrangian, which itself is the difference between the system's kinetic and potential energy. This formulation, known as Hamilton's principle, not only streamlines the analysis of mechanical systems but also serves as a foundational pillar for more advanced theories in physics, including quantum mechanics and field theory. Conceptually profound and mathematically powerful, the principle encapsulates nature's intrinsic tendency to follow paths of optimal behavior, revealing deep connections between symmetry, conservation laws, and the dynamics of motion.
The variational principle in classical mechanics has its intellectual roots in the 17th century, when scholars began to interpret natural phenomena through the lens of optimization and economy. One of the earliest and most influential formulations came from Pierre de Fermat, who in 1662 proposed the principle of least time in optics. Fermat asserted that light, when traveling between 2 points, selects the path that requires the shortest time, a concept that elegantly explained the laws of reflection and refraction. This idea was revolutionary not only for its predictive power but also for its philosophical implications. It suggested that nature operates with a kind of intrinsic efficiency, choosing paths that minimize certain quantities. Fermat's principle was later generalized and formalized by other thinkers, including Johann Bernoulli, who tackled the brachistochrone problem in 1696, and Pierre-Louis Maupertuis, who in the mid-18th century introduced the principle of least action in mechanics. Maupertuis argued that all physical processes follow paths that minimize a quantity called action, reinforcing the notion that nature is governed by optimality. These developments laid the groundwork for the powerful variational formulations of mechanics developed by Euler and Lagrange, which ultimately culminated in Hamiltonian mechanics, a framework that remains central to modern physics, from classical dynamics to quantum theory.
The solution to the brachistochrone problem, a challenge posed by Johann Bernoulli in 1696, is the cycloid, a curve traced by a point on the rim of a rolling circle. This curve represents the path along which a particle, sliding frictionlessly under gravity, will reach the lowest point in the shortest time. Remarkably, the cycloid is faster than a straight line or any other conceivable path, even though it initially dips more steeply. The problem was pivotal in the development of the calculus of variations, and its solution was independently discovered by several great mathematicians of the era, including Newton, Leibniz, and the Bernoulli brothers. The evolution of the variational principle in classical mechanics reflects a profound journey from philosophical intuition to rigorous mathematical formalism. In the 1740s, Pierre-Louis de Maupertuis, though his formulation lacked mathematical precision, it was groundbreaking in shaping the Enlightenment-era view of the universe as governed by harmony and economy. Building on this conceptual foundation, Leonhard Euler and Joseph Louis Lagrange provided the principle with a solid mathematical structure. Lagrange, in particular, reformulated mechanics using a scalar function known as the Lagrangian, minus the difference between kinetic and potential energy, and derived the Euler-Lagrange equations through the newly developed calculus of variations. This approach not only generalized Newton's laws but also allowed for greater flexibility in choosing coordinate systems, making it applicable to a wide range of physical problems. In the 19th century, William Rowan Hamilton refined the variational framework by introducing the action integral and articulating Hamilton's principle, which states that the true path of a system is the one that makes the action stationary. Hamilton's formulation unified and extended earlier work, laying the groundwork for modern theoretical physics, including quantum mechanics and field theory. Hamilton's principle asserts that the actual path taken by a physical system between two states is the one that renders the action stationary, typically minimized, offering a profound shift from force-based descriptions to a more holistic view of motion. This principle elegantly unifies diverse aspects of classical mechanics by framing dynamics through the calculus of variations, where the action, defined as the integral of the Lagrangian over time, governs the system's evolution. Beyond its classical roots, Hamilton's principle laid the conceptual foundation for Feynman's path integral formulation in quantum mechanics, bridging deterministic trajectories with probabilistic amplitudes. What began as an intuitive idea that nature favors efficient paths has matured into a rigorous mathematical framework that underpins much of modern theoretical physics, from field theory to general relativity, revealing the deep symmetries and conservation laws that govern the universe.